All right, let's look at the first problem. In this problem, we're going to find a current I/O in the network. So the current I/O is over here. Look at the current in the problem, and we have Ix that here, and we have like one dependent source over here, and this dependent source depends on the current Ix. So it looks like if I look at this whole problem together, I have like already got two currents that I don't know. If you want to use KCL, like what we did from last week, we said if you are trying to find the current, and you can potentially use KCL to find the equation. For this circuit, we have one node here, one node down here. So we can pick one node to write the node equation. Then we'll be able to find a relationship between IO and IX. And on top of that, we can try to find a relationship between this current and this current by looking at their resistance relationships. All right, let's do that. So the first step, so step one, we're gonna apply KCL to a node. So let's say I'm gonna define this as my node A.
Is it okay instead of figuring out the KCL equation, you make the diagram smaller by reducing those circuits with the one that's in parallel plus series? Like, can you redraw the diagram first? Is that okay to do instead of applying KCL first? I just, just approach-wise, I don't want to approach it wrong. Like, you should be doing KCL before you try to change the circuits diagram,
Try to simplify the circuit, you mean, right?
Yes.
Yeah, you can simplify the circuit the first. It doesn't matter over here. That's a good question. So it doesn't matter. So you can simplify the circuit to say, like, I want to simplify the circuit first. That is also okay.
Okay, thank you.
When you simplify circuit, you have two resistors in parallel, and there's another resistor in series. But make sure you keep track of the current going through that branch, because when you combine the two together, it means that you will lose that current Ix. You have a different current. Yeah.
Professor, what if I will just find the current flowing through the 6 kilo ohm, because we can't find the relationships V1 equals to V2, and then that's what I did. I found another one, and then the current.
Yeah, we can do that as well. For example, we're going to use the current divider is a current division relationship to find the current in this branch, basically, right? This is the current in this branch. So the current in that branch will give it a name, say like this is my current I1. Let's say this is our current I1. And by using the current division relationship, or you use Ohm's law, say the voltage between these two nodes will be the same, and the voltage between these two nodes that is equal to 3 times Ix. So 3 times Ix, that is equal to the voltage drop between this node and that node, right? Because it's the same node pair. So that is 6 times I. So you can do that. So from there we can find I that is equal to 0.5 Ix. And from there, we can also find the overall current to this branch as well. So the overall current, let's call it I2 then. Let's call the current over here I2. So we'll be able to find I2 that is equal to basically Ix plus I1, right? So that is 1.5
Ix.
Yes. At the same time, the overall resistance for the network, we also know that, right? The overall resistance for the network. Let's give it a name. So I say block 1 then. So when I say block 1, it means here. So I'm going to give it a name, block 1. So the overall resistance for that is equal to, and 4 in parallel with, 4 in series with 3 and 6 in parallel. So it's like 4 in series with another 2 resistors. So that'll be 4 plus something. And these 2 in parallel, so that'll be 3 and 6 in parallel. 3 and 6 in parallel, we can find it by using 3 times 6 over 3 plus 6.
It would be 6.
What do you say? So, oh yeah, that will be equal to 6 kilo ohm. So from there, we can also find a relationship between IO and this I2, right? because this R1 is equal to 6 kilo ohm, and this is equal to 3K. So it means we can find one relationship already, right? So this is a half of that. So the current IO is 2 times of that. So we can find the relationship because these two branches in parallel. So the current IO is equal to 2 times of. If you don't cannot see it right away, we will just write it by using Ohm's law. Say IO times this is 3 kilo ohm. That will be equal to the current I2 times the overall resistance. So basically, we calculate the voltage by using Ohm's law. So you can simplify this a little bit. That will give us, because R is equal to 6, I2 that is equal to 1.5 Ix. So we can find IO that is equal to 2 times of Ix. Find one relationship already. But to solve the two unknowns, we need two equations. So the second equation will come from this step 4. We're going to write an additional equation about this node A. So if we do that, you can define your node A over here as well. So it doesn't really matter. So if you do it on the top, that may be a little bit easier because you have only one branch over here, but now you have 2 branches. So we write a KCL equation about this node.
Professor, isn't I not 3ix?
So this is 3, this is 6. 6 divided
You have
by...
1.5 there.
Oh, yeah, you're right. 2 times 1.5, this is 3 times Ix. Yeah, you're right. Yes, good catch. Thank you. So the second equation comes from the node KCL equation at this node. So we write it out, say like, let's use the current that goes into the node as up to 0. We have I0. This is a 2Ix. Next branch is Ix. This branch is 0.5Ix, because we can also see these two as one giant branch. So that will be I2, that is a 1.5Ix. So 1.5Ix. And the last one is leaving the branch, so minus 6, that is equal to 0. So step 5, we'll combine and solve the equations. We'll solve these two equations. One is like that. This one will be over here. So we can find IO or IX. We can find them at the same time. So let's plug this in. So this is 3.5 Ix, and this is 3 Ix, so 3.5 and 3. So that's a 6.5. That is equal to 6. So we can find Ix, that is a 6 over 6.5. So that's a 12 over 13 milliamp. So we can find IO, that is a 3 times of that. That'll be a 36 over 13. All right, any questions? So this problem looks complex, but if you just sit down and use like the resistor in parallel and a series, and you will be able to find the relationship slowly. And the first equation, or in this case, we put it here since step 4, that is the equation from the KCL. You can apply it at this node or at that node. The next example, we're going to find out the overall resistance of a network. If you can see the connection, say like from here, then this will be, and this will be something that I want to solve first. Say I'm going to call this as my block 1. So I'm going to find the resistance for this block 1 first. Then I will simplify the circuit network. I will write the resistance for block 1. And inside this block 1, we have a resistor with a resistance of 2K, and in series with 3 and 6 in parallel. So that will give us a 3 and 6 in parallel. That is a 2 ohm plus 2 ohm. That is a 4 kilo ohm, 4 kilo ohm. And you can simplify the resistor network. So I'm going to replace this block by one resistor. So you're going to simplify that whole thing, and you're going to add another resistor over here. And that resistor is R1. Then you will be able to find RAB, right? So then we can find the resistance for the whole network, RAB. This is the resistor network, RAB. We have like 1K in series with this 4 and R1 in parallel. So 4 and R1 in parallel. And we already know that R1 is equal to 4, and 4 in parallel with 4, that is 2. 2 plus 1, that is 3 kilo ohm. So that is how we solve this problem. So for the next problem, actually this problem is probably similar to the previous one. We'll do it block by block.
Can I see the end again of that?
You get it?
Yeah, okay, I see.
I got a quick question.
Yes.
So right there where you we put R1 equals 2 plus the 1 over 3 and 1 over 6. Why did you choose 2 to be the parallel to 3 and 6? Is it because of the shape and how it is?
2 is not in parallel with them. 2 is in series with them. So look, between these two nodes, 1 and 2, these two nodes, these two are parallel, right? Because they're connected to these two nodes.
Oh,
And this
okay. So
whole thing is in series with this branch. They're connected between these nodes, two nodes. So if we look at these two nodes, basically between these two nodes, there are two branches. One branch has 4K, the other branch is this whole thing.
okay, I see. So look at the nodes.
Yeah, look at the nodes. So we're going to talk about an easier method to deal with this though. So this is typically how you're going to do it. And also typically like the textbook will tell you this is the way how to do it. But I'm going to teach you a different way to do it and it will be a lot easier.
Cool.
So I'm going to do that for the last example. So for the second example, because this is easy to see the connection, so we don't need to bother using the method that I'm going to teach you. So we're going to do this the same thing, and we're going to do it block by block. So this block, if we can simplify this block to one resistor, so that'll be the problem will be gradually simplified. So we will first calculate the resistance for this block 1 then. So we'll say like the resistance for block 1, call it R1. And inside this block, between these two nodes are going to be something that we're going to plug back into the circuit, right? So that is this 4K in parallel with the rest. So that is equal to 4K in parallel with the other two in series. These two in series. So that is a 2 plus 2. So whenever in series, that's a plus. So that is a 2 kilo ohm. Similarly, we're going to simplify this bigger block. So if you want to simplify the circuit diagram, we will do that because we're going to take off this whole thing, right? And at the same time, we're going to plug this R1 back in there. And this is our R1. So R1 is equal to 2 kilo ohm. So then the problem is gradually simplified. We can do something similar to what we did before. And we say, let's simplify this network and I call this the block R2. So we're going to find the resistance for block R2. We'll call it a block R2. So block R2, let's look at this. It has a one branch 12 in parallel with the rest, right? So that is a 12 in parallel with the other two in series. So that is 2 plus R1. R1 is also equal to 2. So that is a 12 in parallel with 4. So that is 3 kilo ohm. So that is how we find the resistance for this block. And after that, everything becomes pretty straightforward. So if we replace that whole thing, and the circuit diagram become like gradually simplified with only one resistor there. And this resistor is called R2, basically R2. Now we can find RAB. So typically in the second step, you can do the whole thing because in the second step, you will be able to see the connection already. You see 9 in series with the rest. So RAB, that is equal to 9 in series with R2. R2 is equal to 3, so that gives us a 12 kilo ohm. So this is how we solve this problem. So you do it step by step. This works well for circuits that you can see the connection right away. But just now, as another student raised a question, say like, how do you know the connection? What if I cannot see the connection right away? For example, this is circuit. Do you know the relationship between this 2K and the other 12K? It's not that easy, right? Just assume that I cannot see the connection right away. So this is something I'm going to do it. I'm going to label all the nodes. For example, this is node A, and I know that this is the same node, right? So I'm going to put that as node A as well. So this is my node A. At the same time, this node B, and I know that these are all connected to B. So this is my node B as well. And this is my node B. And this is also my node B, right? Because all these are connected to the same node without any elements in the middle. So there's only one additional node that is not defined, so which is over there. So I'm going to go ahead and define that as C. So I'm going to define this node as my node C. The purpose to do this is basically to find this equivalent circuit so that I can see the connection in an easier manner. The problem for this is to find the connection between A and B. So first I want to see like whether there are any direct connections between A and B. assume this is my node A, and this will be my node B. Are there any direct connection between A and B? How many? So let me do some activity. So key your question in chat, but don't hit enter until I tell you to. The question is, how many branches between A and B? I want you to put your answer in chat until I tell you to hit enter, then you will all hit enter. Are you ready? My question is, how many branches between A and B directly? So the direct connection. All right, hit enter. Oh, cool. Majority of you find out 2 branches, and some of you find 1 branch, and some of you find only, some of you find 3. So let's look at this. It doesn't matter like it's right or wrong, because we are still in the learning process. So I just want you to participate. Between A and B, this is 1 branch, right? So look, between A and B, there is 1 branch that's pretty clear. And another branch is over here. Look, A, B. I'm not sure how did you find the third? There's no third, right? Maybe you think that the rest will be the third. Say like has to go through C before you can touch B. You can think of it that way. So I'm gonna draw the branches between A and B directly first. So I have a 4K over here. I know that is there. There is already 1 branch between A and B. So it's from here A and I connect it to B, right? And this is 4K. We already know that. So we get this 4K. So in your problem, you can mark this down. So we already get this. The second branch is between A and B, but it's a 12K. It's this branch. So I'm gonna do the same thing to the second branch. This is 12K. So it's better for us to mark it. So let's say this is 4. I'm gonna basically like omit the units so that it will make the problem a little bit cleaner. But we know that all the units are kilo ohm. So this one is a 12K. So there are no other direct connections between node A and B, right? Then we need to find the connection between A and C before we touch any other branches, right? So between A and C, how many branches? There are only 1, right? A, C. I don't see any other branches that are connected between A and C. So between A and C, there is 1 branch. It has a resistance of 2K. So this is our 2K. So now this is our new node C. So this is my node C, basically. Between C and B, how many branches? 1, 2, and no others, right? You cannot go backwards because we already counted that, right? You cannot go backward to there. We did that already. We count from A. We want to go to B. So between C and B, there are only 2 branches. One is 6, the other one is 12. So we're going to draw 2 branches there. Between C and B, we have 2 branches. This is my B, right? Everything on the bottom, that will be my B. Everything on the top, that is my A. So now we get our equivalent circuit. Take a look at the problem again, so you will be able to see the connection right away, right? So the 2 resistors are, one is a 6, the other one is a 12. Now I would assume that all of you should be able to simplify the resistor network, right? Anyone have a question, by the way?
No.
So let me see chat. Then the next step will be able to simplify this step by step, right? So I'm going to simplify the block 1. I'm going to do the same thing. I'm going to pick a easier block to work with. So say like this is my block 1. So I'm going to say find the resistance of the block 1. Let's call it R1. The resistance in block 1 that has 2 in series with 6 and 12 in parallel, right? So that is 6 and 12 that in parallel, that is 4. 4 plus 2, that is 6. Then we can do the rest, because the rest we have like 4 in parallel with 12, then in parallel with R1. So we'll be able to find RAB 4 in parallel with 12, then in parallel with R1. So 4 in parallel with 12, that is 3. 3 in parallel with 6, that is 2 kilo ohm. Right, that's how we solve the problems.